Swayam Prabha. Digital India. Educated India.
Having established that non-inertial frames do provide, particularly in this case uniformly moving non-inertial frames do provide a method of solving problems in an easier way, we will now solve a few examples. Most of them will be from the book of Kleppner. So, we are going to solve illustrative problems. Problem 1. This is taken from the book of Kleppner, whose reference I have already given you. If I have a car moving with acceleration a to the right and it has a rod on the pivot of length L and mass m, we want to find at what angle from the top of the car would it balance and what happens when it is moved from that balance point slightly. So, let us first calculate angle theta at which the bar is balanced. We have already established that going to a uniformly moving frame makes problems easy. So, we will be solving this problem in a uniformly moving frame which is attached to the car and therefore accelerating to the right with acceleration a. When the rod is in equilibrium in this uniformly moving accelerating frame, it is under equilibrium, it is in equilibrium under the forces of mg. And as I have already argued, I can think of the fictitious force ma like an effective gravitational force which is working in the direction opposite to the direction of acceleration of the frame, and it also acts on the center of gravity. So, it is under the influence of m a to the left, and there are normal reactions at the pivot. Let us call this n1 to the right and n2 vertically up. So, this rod is under equilibrium, in equilibrium under these forces minus ma, n1, n2 and mg. Let us go to the next page and show this free body diagram of the rod again. It has a force mg acting downwards, a force ma working to the left, normal reaction n1 working to the right, normal reaction n2 working to the vertically up, and summation fx equals to 0 gives me n1 equals m a, summation fy equal to 0 gives me n2 equals mg, and summation torque about pivot gives me, if this angle is theta and the length of the rod is L, it gives me L over 2 sin theta times m a minus mg times L over 2 cosine of theta equal to 0. M drops out, L by 2 drops out, and that gives me tangent of theta equals g over a. So, the rod is at an angle theta such that tangent theta equals g over a from the horizontal. What direction is this? Recall earlier I had told you, if there is an acceleration and there is g, then the effective gravitational field is this one, the sum total of the two at this angle, which is tangent theta equals g over 2. So, it is not surprising that the rod is in equilibrium precisely aligned up with the direction of the effective gravitational field. It is like an inverted pendulum. Right? It is like a pendulum you can sort of put pointing up, and that will also be in equilibrium. However, inverted pendulum is in unstable equilibrium. If you just disturb it slightly from the equilibrium point, it takes off. So, this rod should also be in an unstable equilibrium. Let us see that in the next part of the problem. So, in part B, we see what happens to the rod when it is disturbed from its equilibrium position. So, the rod is at an angle theta from the horizontal or from the top of the car, and what we do now is disturb it slightly by an angle phi. What happens then? Naturally, there is a force ma working to the left, mg pulling it down, and if I write the equation for theta plus phi about the pivot point here, let us see what that equation looks like. So, that equation is going to look like I, where I is the moment of inertia of the rod about the pivot point, theta plus phi double dot, which is nothing but I phi double dot, theta is a given fixed angle, is equal to, phi is going this way positive. So, it is going to be equal to m a L by 2 sine of theta plus phi minus mg L by 2 cosine of theta plus phi. Let us expand this. When we expand this, we are going to get m L by 2 can be taken out, a sine theta cosine phi plus a cosine theta sine phi minus g cosine theta cosine phi plus g sine theta sine phi. Let us take phi to be very small, so that sine phi is almost phi and cosine phi is 1, and therefore, I get I phi double dot is equal to m L by 2 a sine theta plus a cosine theta times phi minus g cosine theta plus g sine theta times phi. Recall, tangent theta is g over a, and therefore, cosine theta is equal to a over square root of g square plus a square, and sine theta is g over square root of g square plus a square. Let us substitute that, and then we get I phi double dot is equal to m L over 2 a sine theta is g over square root of g square plus a square plus a cosine theta is A over square root of g square plus a square phi minus g cosine theta is a over square root of g square plus a square plus g sine theta is g over square root of g square plus a square phi. This term cancels and you get this is equal to m L over 2 square root of g square plus a square times phi. And therefore, the equation when the rod is disturbed from its equilibrium position is I phi double dot is equal to m L by 2 square root of g square plus a square phi, or phi double dot minus m L over 2 I square root of g square plus a square phi equal to 0. And the solution of this we have already seen in many examples is of the form phi equals a e raised to lambda t plus b e raised to minus lambda t, where lambda square is ml over 2I square root of g square plus a square. So you can see with time the solution is going to grow, phi is going to grow, and therefore the equilibrium is unstable. Problem number 2 we do, suppose I have a car whose door is open at the right angle to the car, and suddenly the car accelerates to the right with an acceleration a. I want to find, as the door swings back, when it has swung by an angle theta, what is its angular speed. As I said earlier, it's best to go to an accelerating frame in this case, and you will see that the door hinged here is sort of moving in a gravitational field with a force ma being applied at its center of gravity. At an angle theta, the force acts as a center of gravity on this side ma. If the width of the door is w, then the distance from the hinge to the force, if it has moved by an angle theta here, is w by 2 cosine of theta. And therefore, the equation of motion of the door in the accelerating frame is going to be I, where I is the moment of inertia of the door, theta double dot is equal to m a w over 2 cosine of theta. Again writing theta double dot as 1/2 d over d theta, theta dot square, we get I theta dot square divided by 2 as equal to m a w over 2 sine theta plus a constant, but theta dot square is equal to 0 for theta equal to 0, and therefore I theta dot square over 2 is equal to m a w over 2 sine of theta, and that gives you the angular velocity of the door at an angle theta when the car starts accelerating towards the right. There is a nice interpretation of this, and you will see that really the interpreting of this force, fictitious force ma, like a gravitational field, makes sense. When this is moving towards the right with acceleration a, we can consider this door to be in a gravitational field with the gravitational acceleration a. By the time the door has swung by an angle theta, its center of mass has come down by this much distance here, and that distance that it has traveled along the direction of minus a is nothing but w over 2 sine of theta, and therefore change in its potential energy is equal to m a, which is the force, times w over 2 sine of theta. It is by that much that its potential energy has decreased, and therefore the increase in the kinetic energy should be precisely that, m a w over 2 sine of theta, and that is your answer. By the time door shuts, that is, it comes all the way back, then theta equals pi by 2 for door to shut. So it shuts at an speed theta dot square, which is equal to 2 m a w over 2 I, 2 cancels, equals m a w over I. That gives you the angular speed with which the door shuts. That's another example of solving the problem using accelerating frames. As a third problem, I take a problem that you must have seen sometimes. Sometimes you must have seen that if you have a motorcycle and the rider accelerates it suddenly at a very high acceleration, then you see it tends to topple. The front wheel sort of lifts off the ground, and we want to calculate as to at what acceleration does it start lifting off the ground. I am again going to look at this problem from a frame which is accelerating with the motorcycle towards the right with A. If it does that, then the motorcycle is in equilibrium, it is not moving in that frame, and if I look at the motorcycle, it is in equilibrium under the following forces. There is a force N2 on the back wheel, normal reaction N1 on the front wheel. There is a frictional force F1 on the front wheel. There is a frictional force F2 on the back wheel. There is a fictitious force working out the center of gravity towards the left, MA, and at the center of gravity there is a force, gravitational force, mg. Let us take the height of the center of gravity from the ground to be h, and let us take the distance between the two wheels to be b. We wish to calculate as to at what acceleration does the front wheel start getting off the ground. So, in this accelerating frame, the motorcycle is in equilibrium under these forces. Let us write the equilibrium conditions. You get summation Fx is equal to 0, which gives me F1 plus F2 equals ma. Summation Fy equals 0 gives me N1 plus N2 equals mg. And the torque about any point should be 0. Let us take for convenience the torque about the center of gravity. Let me make the picture again for you in the next page. Here is the motorcycle with distance b here, center of gravity being at height h from the ground. There is normal reaction N2, N1, there is friction F2, F1, and there is this force at the center of gravity ma and mg, and we have already found that F1 plus F2 equals ma and N1 plus N2 equals mg, and balancing the torque about Cg equal to 0 gives me F1 plus F2, which is a counterclockwise torque, times h equals N2, which gives you a clockwise torque, minus N1, minus because N1 gives you a counterclockwise torque, times b by 2, if I assume that the center of gravity lies right in the middle of the two wheels. And therefore, substituting F1 plus F2 equals ma, mah equals N2 minus N1 b by 2, or N2 minus N1 equals mah times 2 divided by b, and I already know that N2 plus N1 equals mg. I have got these two equations to solve for N2 and N1. So, let me show again. Here is the motorcycle, here is the center of gravity, here is reaction N1, here is reaction N2, and we have found that N2 minus N1 is equal to 2 mah over b, and N2 plus N1 is equal to mg, and that gives you n2 equals mg over 2 plus mah divided by b, and n1 equals mg over 2 minus mah divided by b. When the front wheel lifts off the ground, n1 equals 0, and that gives you mg over 2 minus mah over b equals 0. M drops out, and therefore A equals, you have mg over 2 minus mah over b equal to 0. M has dropped out, so A equals gb over 2h. If the acceleration is gb over 2h, the front wheel would start lifting off the ground. So if you keep acceleration below this, the front wheel doesn't go up. Similarly, if you decelerate, exactly opposite would happen. The rear wheel would start coming off the ground. That I'll leave for you as a problem. To conclude this lecture, what we have done today is looked at solving the problem in a uniformly accelerating frame. In the coming lectures, we will go to another kind of non-inertial frame, which is a rotating frame. Our Earth is one example of that, and see the consequences of that.